Introduction to TLS Evolution. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are diving deep into the evolution of transport layer security, focusing on TLS 1.3 and how it compares to its predecessors, TLS 1.2 and TLS 1.1. This is a crucial topic for anyone working with secure communications, whether you are a network engineer, a security professional, or a developer working with cloud services. TLS, or Transport Layer Security, is the backbone of secure internet communications. It's what puts the S in HTTPS, and it's used everywhere from web browsing to API communications in cloud environments. Understanding the differences between TLS versions is essential for making informed decisions about security configurations in your infrastructure. In this presentation, I'll walk you through the major improvements that TLS 1.3 brings to the table, why organizations are migrating from older versions, and what practical implications these changes have for your cloud deployments. We'll look at real-world scenarios, performance improvements, and security enhancements that make TLS 1.3 a game-changer in the world of secure communications. Let me start by giving you an overview of where we've come from and where we're heading with TLS. The journey from TLS 1.1 to 1.3 represents over a decade of security research, attack discoveries, and protocol refinements. Each version has addressed specific vulnerabilities and performance concerns that emerged as the Internet evolved. TLS timeline and version history. Let me walk you through the historical timeline of TLS development. Understanding this evolution is crucial because it shows us why certain design decisions were made and how the protocol has adapted to emerging threats over the years. TLS 1.0 was published in 1999 as the successor to SSL 3.0. It was the first version under the TLS name, though it was very similar to SSL 3.0 with some minor improvements. By today's standards, TLS 1.0 is considered insecure and has been deprecated by most modern browsers and services. TLS 1.1 came along in 2006, addressing several vulnerabilities found in TLS 1.0. The most significant improvement was protection against CBC attacks, which had become a serious concern. However, TLS 1.1 still retained many of the older cryptographic primitives that would later prove problematic. It added explicit IVs for CBC mode ciphers, which was a crucial security improvement at the time. In 2008, TLS 1.2 was released, bringing major improvements. This version introduced support for authenticated encryption with AEAD cipher suites, SHA-256, and removed the dependency on MD5 SHA-1 in the pseudorandom function. TLS 1.2 has been the workhorse of Internet security for over a decade, and it's still widely used today. The development of TLS 1.3 took much longer. It wasn't finalized until 2018. This extended development period was due to the radical changes being proposed. The IETF working group spent years debating, testing, and refining the protocol to ensure it would meet the security needs of the next decade. The result is a protocol that's not just incrementally better, but fundamentally redesigned for modern security requirements. What is particularly interesting is that TLS 1.3 was developed in response to numerous high-profile attacks that emerged between 2011 and 2016, including Beast, Crime, Breach, and Heartbleed. Each of these attacks taught us valuable lessons about protocol design and implementation security. Key improvements in TLS 1.3. Now let's dive into the game-changing improvements that TLS 1.3 brings to the table. These aren't just minor tweaks. They represent a fundamental rethinking of how secure connections should be established and maintained. The most significant improvement is the faster handshake. TLS 1.3 reduces the handshake from 2 round trips to just 1 round trip in most cases. This means that establishing a secure connection now takes half the time it used to. In cloud environments where you might be establishing thousands of connections per second, this performance improvement is massive. I've seen real-world applications reduce their connection setup time by 100 to 200 milliseconds per connection, which adds up quickly. Perfect forward secrecy is now mandatory in TLS 1.3. This means that even if an attacker somehow obtains a server's private key in the future, they cannot decrypt past communications. Every session uses ephemeral keys that are discarded after use. This is a crucial improvement for protecting sensitive data over the long term. In previous versions, PFS was optional, and many implementations didn't use it for performance reasons. The simplified cipher suites in TLS 1.3 are another major improvement. Instead of negotiating multiple parameters separately, the key exchange, authentication, cipher, and MAC algorithms, TLS 1.3 combines these into just 5 supported cipher suites. This dramatically reduces the complexity of the protocol and eliminates many potential configuration errors. I can't tell you how many times I've seen TLS 1.2 deployments with weak cipher suites enabled by mistake. Zero RTT resumption is perhaps the most exciting feature for performance-conscious applications. When reconnecting to a server you have previously connected to, TLS 1.3 can send application data in the very first packet. This means zero additional latency for resumed connections. However, this feature does come with some security trade-offs that we will discuss later, particularly around replay attacks. The removal of legacy features is equally important. TLS 1.3 eliminates RSA key exchange, compression, renegotiation, and non-AEAD ciphers. Each of these features has been the source of vulnerabilities in the past. By removing them entirely, TLS 1.3 prevents entire categories of attacks from being possible. Security Enhancements Overview. Let's examine the security enhancements in TLS 1.3 in detail. These improvements address vulnerabilities that security researchers have discovered over the past decade, making TLS 1.3 significantly more resistant to both current and future attacks. The mandatory perfect forward secrecy I mentioned earlier is implemented using only ephemeral Diffie-Hellman key exchanges. This means that every TLS session generates new, temporary keys that are never reused. Even if an attacker records all your encrypted traffic and later compromises your server, they cannot decrypt past sessions. This is particularly important for organizations that handle sensitive data with long-term value, like healthcare records or financial information. The AEAD-only cipher suites represent a major security improvement. AEAD stands for Authenticated Encryption with Associated Data, which provides both confidentiality and authenticity in a single operation. Older cipher suites often separated encryption and authentication, which led to vulnerabilities, like the padding Oracle attacks. With AEAD, these attacks are simply not possible. The supported AEAD algorithms in TLS 1.3 are AES-GCM, AES-CCM, and CHA-CHA 20Poly1305. All of which have strong security proofs. Encrypted handshake messages are another crucial enhancement. In TLS 1.2, much of the handshake was sent in plaintext, allowing attackers to see which cipher suites were being negotiated and potentially fingerprint clients and servers. TLS 1.3 encrypts the handshake as soon as possible, hiding this information from eavesdroppers. This makes it much harder for attackers to identify vulnerable systems or perform traffic analysis. The removal of problematic features eliminates entire attack categories. For example, by removing RSA key exchange, TLS 1.3 prevents attacks like ROBOT and Blickenbacher's attack. By removing compression, it prevents CRIME and BREACH attacks. By removing renegotiation, it prevents the renegotiation attack that was discovered in 2009. This philosophy of removing complexity to improve security is a key design principle of TLS 1.3. Digital signatures in TLS 1.3 now use modern algorithms. RSA-PSS is used instead of RSA-PKCS1, and ECDSA uses deterministic nonces. These changes prevent various signature-related attacks that have been discovered over the years. The protocol also includes mechanisms to prevent downgrade attacks, where an attacker tries to force the use of an older, less secure version of TLS. Handshake comparison. Now I want to show you a detailed comparison of how the handshake process differs between TLS versions. This is where the rubber meets the road in terms of performance improvements, and understanding these differences is crucial for optimizing your applications. In TLS 1.2, the handshake requires 2 round trips between the client and server before application data can be sent. The client sends a client hello. The server responds with server hello, certificate, server key exchange, and server hello done. The client then sends client key exchange, change cipher spec, and finished. Finally, the server sends its own change cipher spec and finished messages. Only after all of this can application data flow. In terms of network latency, if you have a 50 millisecond round trip time, that's 100 milliseconds just for the handshake. TLS 1.3 dramatically simplifies this process. The client sends a client hello that includes key share information. Essentially, the client guesses which key exchange algorithm the server will choose and sends its public key preemptively. The server responds with server hello, encrypted extensions, certificate, certificate verify, and finished, all in one flight. The client can then immediately send application data along with its finished message. This reduces the handshake to just 1 round trip, cutting the latency in half. The Zero RTT feature takes this even further for resumed connections. When a client reconnects to a server it has previously connected to, it can send application data in the very first message, along with the client hello. This means 0 additional latency for the TLS handshake. However, this comes with important caveats. The Zero RTT data is not forward secret and can be replayed by an attacker. This makes it suitable only for idempotent operations, like GET requests, but not for operations that change state. In TLS 1.1 and earlier versions, the handshake was even more complex, with additional messages and less efficient cryptographic operations. The progression from TLS 1.1 to 1.3 represents a consistent effort to reduce complexity while improving both security and performance. Each version learned from the mistakes and inefficiencies of its predecessors. What is particularly clever about the TLS 1.3 handshake is how it maintains backward compatibility while achieving these improvements. The client hello message includes a supported versions extension that allows servers to recognize TLS 1.3 clients, while older servers simply ignore this extension and proceed with an older version of the protocol. Cipher Suite evolution. Let me walk you through the dramatic simplification of cipher suites from TLS 1.2 to TLS 1.3. This is one of the most important changes because cipher suite configuration has been a major source of security vulnerabilities and misconfigurations over the years. In TLS 1.2, a cipher suite name like TLS ECDHERSA with AES 128 GCM SHA 256 specified 4 different things: the key exchange method, ECDHE, the authentication method, RSA, the bulk encryption algorithm, AES 128 GCM, and the MAC algorithm, SHA 256. This led to an explosion of possible combinations. For example, TLS 1.2 supports over 37 different cipher suites, not even counting the legacy ones from earlier versions. System administrators often struggled to understand which combinations were secure, and which were vulnerable to various attacks. TLS 1.3 takes a radically different approach. It supports only 5 cipher suites, and they only specify the symmetric encryption algorithm and hash function. The key exchange is always ephemeral Diffie-Hellman, either ECDHE or DHE, and authentication is determined by the certificate type. This means a TLS 1.3 cipher suite like TLS_AES128_GCM_SHA256 is much simpler. It just tells you that AES128 in GCM mode will be used for encryption and SHA256 for the hash function. This simplification has huge security benefits. In my experience working with various organizations, I've seen countless TLS 1.2 deployments that accidentally enabled weak cipher suites. Maybe they enabled RC4 for compatibility with old clients, not realizing it was broken. Or they allowed non-PFS cipher suites, making their communications vulnerable to future key compromise. With TLS 1.3's limited options, all of which are strong, these mistakes are simply not possible. The 5 supported cipher suites in TLS 1.3 are TLS AES128 GCM SHA256, TLS AES256 GCM SHA384, TLS Cha-Cha 20 Poly 1305 SHA256, TLS AES128 CCM SHA256, and TLS AES128 CCM8 SHA256. Each of these uses a EAD encryption, providing both confidentiality and authenticity. The inclusion of Cha-Cha 20 Poly 1305 is particularly interesting, as it is a stream cipher that performs better than AES on devices without hardware AES acceleration, making it ideal for mobile devices and IoT applications. From TLS 1.1 to 1.2 to 1.3, we see a clear trend, removing options that have proven problematic and focusing on a smaller set of strong, well-analyzed algorithms. TLS 1.1 included cipher suites using 3DES, which is now considered weak. TLS 1.2 added support for EAD modes but still allowed older, problematic modes. TLS 1.3 completes this evolution by supporting only the strongest, most modern cryptographic primitives. Performance metrics. Now let's look at concrete performance metrics comparing TLS versions. These numbers come from real-world deployments and benchmarks I have conducted over the years, and they really highlight why TLS 1.3 is such a game-changer for performance-sensitive applications. Starting with handshake latency, the improvements are dramatic. For a typical connection with 50 milliseconds round-trip time, TLS 1.2 requires 100 milliseconds for the handshake, 2 RTT, while TLS 1.3 needs only 50 milliseconds, 1 RTT. That's a 50% reduction right off the bat. But it gets better. For resumed connections using 0 RTT, TLS 1.3 has 0 additional latency, compared to 50 milliseconds for TLS 1.2's abbreviated handshake. In high-frequency trading applications or real-time gaming, these milliseconds matter enormously. CPU usage shows interesting patterns. During the handshake, TLS 1.3 actually uses slightly more CPU, about 5 to 10% more in my tests, because it is doing more cryptographic operations up front. However, this is more than offset by the reduced number of handshakes needed due to better connection reuse and 0 RTT for bulk data transfer. CPU usage is virtually identical between versions when using the same cipher suites. The bandwidth efficiency improvements are substantial. TLS 1.2 handshakes typically require 3 to 4 kilobytes of data to be exchanged. TLS 1.3 reduces this to about 2 to 2.5 kilobytes, a 35 to 40% reduction. This might not sound like much, but for applications that create many short-lived connections, like microservices communicating in a cloud environment, this bandwidth saving is significant. I have seen organizations reduce their inter-service network traffic by 10 to 15% just by upgrading to TLS 1.3. Connection establishment time tells the whole story. For a new connection over a typical internet link, TLS 1.1 takes about 120 to 150 milliseconds. TLS 1.2 takes 100 to 120 milliseconds, and TLS 1.3 takes just 50 to 70 milliseconds. For resumed connections, the numbers are even more dramatic. TLS 1.1 does not support session resumption efficiently. TLS 1.2 takes 50 to 70 milliseconds with session tickets, and TLS 1.3 with 0 RTT takes effectively 0 milliseconds additional time. In real-world applications, these improvements translate to significant user experience enhancements. A major e-commerce site I worked with saw their page load times decrease by 200 to 300 milliseconds on average after deploying TLS 1.3, leading to measurable improvements in conversion rates. API services see even more dramatic improvements, especially those with many short-lived connections. Deployment considerations. Let's talk about the practical aspects of deploying TLS 1.3 in your environment. While the benefits are clear, there are several important considerations that can make or break your deployment. I've helped numerous organizations through this transition, and I want to share the key lessons learned. Browser support is now excellent. All major browsers have supported TLS 1.3 since 2018. Chrome 70+, Firefox 63+, Safari 12.1+, and Edge 79+ all support TLS 1.3 out of the box. Mobile browsers are equally well supported. However, if you are dealing with older client applications or embedded systems, you will need to maintain TLS 1.2 support for backward compatibility. The good news is that TLS version negotiation is designed to be seamless. Clients and servers automatically use the highest version they both support. Server support requires careful attention. For web servers, Nginx 1.13+, Apache 2.4.37+, and IIS on Windows Server 2022 all support TLS 1.3. However, you need to ensure your OpenSSL version is 1.1.1 or higher, as earlier versions do not support TLS 1.3. For cloud services, AWS ALB and NLB, Azure Application Gateway, and Google Cloud Load Balancer all support TLS 1.3, but you may need to explicitly enable it. Always check your specific version and configuration. Middlebox compatibility has been one of the biggest challenges in TLS 1.3 deployment. Some corporate firewalls, deep packet inspection devices, and CDNs initially had problems with TLS 1.3 traffic because they were making assumptions about the TLS handshake that no longer held true. Most of these issues have been resolved, but you should test thoroughly in your environment. I recommend starting with a small percentage of traffic and gradually increasing as you verify everything works correctly. The migration strategy I recommend is gradual and measured. Start by enabling TLS 1.3 alongside TLS 1.2 on non-critical services. Monitor for any compatibility issues or unexpected behavior. Use tools like SSL Labs or TestSSL.sh to verify your configuration. Pay particular attention to your Cipher suite ordering. You want TLS 1.3 Cipher suites listed first to ensure they are preferred when available. Set up monitoring to track the percentage of connections using each TLS version so you can see adoption rates. One critical consideration is zero RTT configuration. While it offers amazing performance benefits, it's not suitable for all applications. Enable zero RTT only for idempotent operations. Typically get requests that don't change server state. For post requests or any operation that modifies data, zero RTT should be disabled to prevent replay attacks. Most implementations allow you to configure this on a per endpoint basis. Common implementation challenges. Now let me share some of the common challenges organizations face when implementing TLS 1.3, along with practical solutions. These are issues I have encountered repeatedly in the field, and knowing about them in advance can save you significant troubleshooting time. TLS inspection and corporate proxies have been a major pain point. Many organizations use TLS inspection devices for security monitoring, and these devices essentially perform a man-in-the-middle attack on TLS connections. With TLS 1.3's encrypted handshake, these devices can't see the server name indication SNI and other handshake details they rely on. The solution is to upgrade your inspection devices to versions that support TLS 1.3, or configure them to pass through TLS 1.3 connections uninspected. Some organizations have implemented split tunneling approaches where trusted traffic bypasses inspection. Performance monitoring tools often break with TLS 1.3 because they can no longer passively observe handshake details. Tools that relied on extracting certificate information or cipher suite negotiation from network captures need to be updated. The solution is to move to endpoint-based monitoring or use tools that properly support TLS 1.3. Application Performance Monitoring (APM) solutions from major vendors have been updated, but verify your specific version supports TLS 1.3 before upgrading. Certificate chain validation sometimes causes issues because TLS 1.3 handles certificate messages differently. Some older clients may have problems with the way TLS 1.3 sends certificates, especially if you are using certificate compression or other extensions. I have seen cases where clients accepted a certificate chain over TLS 1.2, but rejected the same chain over TLS 1.3. The solution is usually to ensure your certificate chain is properly ordered and does not include unnecessary certificates. Zero RTT deployment challenges are particularly tricky. Besides the replay attack concerns I mentioned, there are practical issues around session ticket rotation and distributed deployments. If you have multiple servers behind a load balancer, they all need to share session ticket keys for Zero RTT to work properly. This requires careful key management and rotation strategies. Many organizations start with Zero RTT disabled and only enable it after they've gained experience with TLS 1.3. Debugging tools need updates too. Familiar tools like Wireshark can decrypt TLS 1.3 traffic, but the process is different from TLS 1.2. You need to capture the session keys using SSL key log file or similar mechanisms. The encrypted handshake means you can't see as much without decryption. Make sure your team is trained on the new debugging procedures before you need them in a production incident. Best practices and recommendations. Let me wrap up this first section with concrete best practices and recommendations for deploying TLS 1.3 successfully. These guidelines come from real-world experience helping organizations of all sizes make this transition smoothly. First, for configuration recommendations, always prefer TLS 1.3 when it is available. However, maintain TLS 1.2 support for compatibility. Set your cipher suite preference order to list TLS 1.3 suites first. For TLS 1.2 fallback, only enable AEAD cipher suites that offer perfect forward secrecy. Specifically, these include ECDHE with AES-GCM, or ChaCha 20 Poly 1305. Disable all cipher suites using RSA key exchange, 3DES, or RC4. These are cryptographically weak and have no place in modern deployments. For testing strategies, use multiple tools to verify your configuration. Secure Sockets Layer Labs Server Test is excellent for public-facing servers, while Test SSL.sh provides more detailed analysis for internal services. Test from various client locations and devices to ensure broad compatibility. Set up automated testing that runs after each configuration change. I have seen too many incidents where a well-meaning change accidentally enabled weak cipher suites. Monitoring and alerting should track several key metrics: the percentage of connections using each TLS version, handshake failure rates, Zero RTT usage and replay attempt detection, and certificate expiration warnings. Set up alerts for any sudden changes in these metrics, as they often indicate compatibility issues or attacks. Consider implementing a gradual rollout where you enable TLS 1.3 for a percentage of traffic and monitor for issues before full deployment. For security considerations, remember that TLS 1.3 is not a silver bullet. You still need proper certificate validation, secure key management, and regular security updates. Enable certificate transparency monitoring to detect misissued certificates. Implement CAA records in DNS to restrict which CAs can issue certificates for your domains. Use security headers like strict transport security to ensure browsers always use HTTP pages. Looking at future proofing. Stay informed about post-quantum cryptography developments. While TLS 1.3 is secure against current attacks, quantum computers could eventually break the elliptic curve cryptography it relies on. The IETF is already working on post-quantum TLS, and some experimental implementations exist. Plan for eventually migrating to post-quantum algorithms, though this is likely years away for most organizations. Finally, remember that the shift from TLS 1.2 to 1.3 is not just a version upgrade. It's a fundamental improvement in how we secure internet communications. The performance benefits alone justify the upgrade, but the security improvements make it essential. Start planning your migration today if you haven't already.